Yes, that's right. We'll be doing the demo or the talk first and then the demo session afterwards. The demo session will consist of, I brought some Arduino kits for y'all to put together, so you have something to look forward to there. So yeah, let's get started. Okay, cool. Hi, I'm Caleb Helbling, and the co-author for this paper with Sam Geyer. We're from Tufts University, and I'm here today to talk to you about Juniper, which is a functional programming language that we've been working on for the Arduino. So just a show of hands, who here has ever used an Arduino for a project? Okay, so quite a few of you. So in case you haven't used an Arduino, or if you have no idea what it is, I have some project ideas here for you. Here's the first one. This is a drink dispensing robot called the Inebriator. This one I found online. I didn't make this myself. Here's another cool idea if you're a cyclist. This is a signaling jacket. So basically, you have turn signals on the back, and then sort of in the middle here, you can see the microcontroller that's used to control everything. Here we have a digital hourglass, which I actually forgot to turn over. Which actually Sam Geyer, who was a co-author of the paper, made this. And I'll be talking a little bit more about that later. This is also the demo and the example in the paper, if you read that. Here is a tree climbing robot that sort of inches its way up a tree. You can see the Arduino is mounted on the back of it. Here's one of my projects, actually. This is a GPS compass watch. So the idea is there's a compass module inside of it, a GPS module, an LED ring, there's a button on the top to control it, and it points you in the direction of the nearest subway stop in Boston. So if you're ever lost, this would be pretty useful. And finally, we have the fire-breathing animatronic pony, which I didn't make, but it kind of shakes its head back and forth and breathes fire. So, yeah. So when we were programming and developing these systems, there's really two parts for this. There's a hardware side and there's a software side. And what we figured would be difficult would be the hardware stuff, because we have no experience with hardware, neither Sam or I do. And we figured once we get to the software side, we'd be home free, because that's totally our domain. And we were really surprised at how bad the situation is. So here's what the Arduino website claims. It's simple, clear, easy to use for beginners, for teachers, for students learning to program. Sounds great, right? No, it's not at all. And the reason is that it's C++. Surprise, everyone. But it kind of needs to be that way. And to see why, let's take a look at the specs on the microcontroller here. So this is an Arduino Uno, which is one of the flagship Arduino products. It has an Atmega 328P microcontroller on it, 8-bit, 16 megahertz, and you may not have heard of this prefix before, but it has 2 kilobytes of RAM. Kilo meaning 1,000, meaning 2,048 bytes of RAM for your program. So as you can tell, that's quite a limited. And also you only have 32 kilobytes to store your actual program. And this is the exact same chip, but on a tiny, smaller device. So you can see that they get very small. So let's take a look at the typical example code that you see with an Arduino, the hello world example, which is turning an LED on and off. So initially we define a global variable to define the LED pin. The setup function is called exactly once. It sets up the pin to be an output mode. And this loop function is called over and over again. It simply sets the digital output pin to high, turning on the LED, waits a second, and then sets the LED to low, waits a second. So it seems pretty simple, right? Let's make it a little bit more complicated. Oh, and this is the exact same code, but just put into a blink function, which we'll use later. So let's add a button to the situation. So the idea here is you have a button, you push the button, the LED turns on, you push the button, the LED turns off. And I'll just walk you through the code again here. So here in the loop function, look for a press by reading the digital pin. If it's high, then wait for the button release, wait until it's low. At that point, on the button release, you turn the LED off if it's on if it's off. Seems simple, and it looks like it should work, but it actually doesn't. Does anybody know why it doesn't work? No. So it turns out that there's actually a physical reason for this not to work. There's something called button bounce, signal bounce, which you may have heard of or may not have. But basically what happens is you have a button, right? And sort of as the metal of the button comes in contact with the base of the button, it sort of jitters a little bit, some electricity leaks through, and the signal just bounces up and down between high and low. And this causes all sorts of issues. In the previous program, it would just cause the LED to flicker like crazy. And there are hardware solutions to deal with this. You can get some like capacitors in your circuit to filter out this sort of signal, but we'd like to deal with it in software. So we have some debounce code here. So this is the isPressed function. First of all, we look for the press. If it's high, then wait 50 milliseconds. If it's still pressed, then continue, then wait for the release, return true, otherwise return false. So this will debounce the button. And here we've implemented this in our main loop in combination with the LED code. So if it's off, turn it on. If it's on, turn it off. So here's another challenge. Get a button which turns a blinking LED on and off. So does this work? We have the blink code and we have the isPress code from before. If we combine those two together, we should get a working program, right? Actually, this isn't the case either. While we're blinking, we use a delay function, so we're stuck there for 2 seconds. So if the button is pressed while the LED is blinking, it won't be registered. And there's another error as well. If we hold down the button, we are stuck waiting for release in a while loop. So clearly, this sort of violates all the good principles of programming that I know about, which is that if you take two functions and you stick them together, you should get a working program. But this is just not the case in this environment. So here's an even simpler example of why this doesn't work. Blink two lights together at different intervals. Will be stuck inside of the blink functions. And on the right here, we can see the code, the C++ code that actually makes it work. And it's pretty ugly. And what happens is you find that when you write bigger C++ programs for the Arduino, you quickly get this sort of spaghetti-like code structure simply because you can't detangle the timing logic from the rest of the logic. So functions that use the delay function don't compose. Combining concurrent activities requires explicit scheduling. Blinking is an ongoing process, so we need concurrency. So what we found is that any reasonably sophisticated Arduino program consists of two things: an ad hoc discrete event scheduler plus some finite state machines threaded throughout the program. And it's actually fairly difficult to implement this in C++ code. It requires quite a bit of thought. So our solution to the problem is to use functional reactive programming to handle event scheduling. And also we use a FRP transformer called foldp, which stands for fold over the past, to simulate finite state machines. And also, since we have pattern matching in the Juniper language, it makes the finite state machines fairly declarative. So if you know this slide's for people who know stuff about functional reactive programming. This is just a classification of where Juniper falls in the FRP spectrum. So Juniper is a higher order discrete impure monadic FRP language, which is kind of a big mouthful. But basically what that means is that we allow dynamic signal graphs. Signals that contain signals are allowed. There's a problem with FRP languages. You often find that they leak space. And obviously, since we only have 2,048 bytes of memory, any space leak would simply be disastrous. So we lose equational reasoning, which we think is a good trade-off for this particular environment. And of course, everything is discrete. So here's a look at some of the language features in Juniper. They're pretty standard for what you would find in functional programming language. We have algebraic data types and all of the rest of the stuff. We also have some imperative features at the bottom. You can see here. We have like while loops and for loops and stuff like that, and also mutable references, which are used occasionally in programming Juniper. And also a big thing when you're programming Arduino code is you have to be able to interact with C++ libraries. So for every hardware device that you want to use with an Arduino, there's a C++ or C library written for it. So it's a big priority to be able to use those libraries in Juniper as well. And for that reason, you can write inline C++ code, and it basically just works. So here's an example of a sort of signal graph, or a definition of what a signal graph is. So the idea here is that events flow along signals, or that signals are time-varying values, and that when they're connected together, they form a directed graph. And the nodes in the directed graph are signal processing functions, like, for instance, map, which takes values on one signal and converts them to another type or another value. As you would expect, you can merge signals. The fold P operator or function that I mentioned before, which we'll see an example in a little bit, and sort of like filtering signals as well. There's a whole bunch of really interesting FRP functions that you can write. So another important consideration to take into account in this environment is the actual way that the signal graph, the directed graph itself, is represented. So there's only 2 kilobytes of RAM. So there's not really enough space to store the data structure, the directed graph data structure, plus all of the necessary runtime components to drive events through the FRP directed graph. So that's kind of out of the picture. One possibility that a lot of other approaches take is using static signal graphs that are known at compile time and using a sort of adjacency list to hook them all together. But our approach is different, which is the signal graph is embedded directly within the call graph of the program. And to see why that's the case, let's take a look at the data type definition of signal. So this definition of signal is really simple. It's just a maybe data type. And the observation here is that at any specific point in time, a signal may have an event or it may not have an event. So we can represent a signal itself as a maybe. And what you find is that these signal processing functions that I mentioned before, like map, for instance, are really map m and maybe monad. So here is the same blinking LED example, but written in Juniper. So you can see that it has sort of an ML style feel to it, and sort of the setup code is very similar. So we start by setting up the board LED to be 13. We set up some states, which are mutable references, and we'll see why those are used in a second. The blink function, which I'll define on the next slide, the setup function, which basically just sets up the pin to be an output pin, and then the main function, which calls a setup function, and while true, do blink infinite loop. So here is the blink function. So every 1,000 milliseconds, we will have a value that travels along a signal called timer sig. The type of the value that travels along timer sig is uint32, and it is a timestamp of the current time. So we pass that signal to the fold P function, which acts an awful lot like the fold L and fold R function that you'll find operating on lists. Basically what it does, it takes in an anonymous function, which it takes in the current time from the timer sig and the last state, which is actually stored in the mutable reference on this slide, the LED state equals ref low. We use a mutable reference to hold the state between the invocations of the fold P function. And at the top, you can see the data type definition of pin state. And toggle will just flip between high and low. And finally, digitally output that signal to the LED pin. Yeah, okay. Any questions so far? No, okay. So I will also talk briefly about compilation. So Juniper compiles to C++ code so that it can run on the maximum number of devices possible. And here is an example of the maybe data type definition compiled to C++ code. And it's a pretty simple mapping. It is basically a templated struct, which has a tag in it and a union. And most of the code here that you see is actually defining the equals function, equals operator, and the not equals operator. And so one of the things that we do in compilation is that each expression in the Juniper language has an exact equivalent expression in the C++ language. And what happens oftentimes in C++ is that things are statements and not expressions like you would want in a functional programming language. So this is a trick that we often use in compilation, which is to define a lambda which is immediately invoked. And we put, in this instance, it's a while true loop. So we just put the loop inside and then return unit at the end. And since the lambda is immediately invoked, this basically converts while into an expression in C++. Very useful. So how am I doing on time? Okay. So the case study is a digital hourglass that we did for, that you can read about in the paper. And as you can see, you might have seen like the setting mode at the beginning. There is actually a capacitive touch button on the top of it to set the amount of time. Actually, I'll just flip it over. There's a pause mode as well, so if you flip it on its side, it kind of blinks on and off. And I'll just reset it here. So you can see that there's a button on the top here that I'm pressing with my fingernail. And every pink dot you see here is 15 seconds. And once you get 15 seconds, it converts to a blue LED, which means 1 minute. And there's also this blinking cursor here. So you can already see that there's a lot of things that are going on concurrently. I have to deal with the button press. I have to debounce the button. I have to turn the LED on and off. I have to make sure that the display is showing the right amount of time. So there's quite a few concurrent activities going on here. And let me just flip this upside down and then clear it. So you can see finale mode. So I set this to be 15 seconds. So it's going quite quickly now. Yay, okay. So there's quite a lot of things that are going on here. And besides all of that, you also have to deal with the accelerometer data. So it's a very concurrent problem. And in the C++ code, it took 950 lines, and it required a lot of thought. And you'll be happy to know that the Juniper code, once it type checked, actually ran without, it worked the first time. So yay, that also seems to work on embedded systems, if you're a fan of that saying. So in conclusion, Juniper is a new FRP language that we designed to work on the Arduino. It has many of the functional programming features that you'd find in most functional programming languages. It compiles to C++, and it shows clear benefits for logic reuse. makes your program smaller and it's easier to write. So thank you. Yeah.
Sounds awesome. But so you say it's a side effectful language, so you have side effects everywhere in the language. Do you have any ideas of plans to possibly add an effect system that tracks which kinds of effects are there, or is that not? Do you think that's not necessary?
So the question is whether or not I'm going to add an effect system to the programming language. Is that right?
Yeah, like extensible effects, like a record kind of thing, or
Yeah. So I actually don't know a whole lot about effect systems, but it seems to work okay right now with the mutable state. It's not like you're mutating things all over the place willy-nilly. It's more like it's just sort of used as a convenience for the signal processing functions. What often happens is that the only mutable variables that are defined are the ones at the top global level. Yeah.
What's the debugging experience? Do you ever find yourself having to go through the C++ code and change that into Juniper code?
So there's actually some issues with the compiler right now. The biggest issue is with numbers, the way that they're represented. We don't have type classes yet. So coercing between different number types is kind of a pain right now. Occasionally I find myself looking through the C++ code if I get a compiler error, but hopefully the compiler is at a state now where it will catch all the errors and the C++ code will just work. Yeah.
So you said you had to give up on equational reasoning.
That's right.
To get to fit to memory, but you didn't explain that at all.
Yeah, so let me go back.
And you didn't even sound embarrassed when you said it.
Yeah. So basically the equational reasoning issue comes up when you have signals of signals. So if you're, so there's this operation called flatten on signals, which basically turns a signal of signal into a signal. And what happens is that basically you have to choose what signal you're listening to based on a value. What happens is that you do have to give up on equational reasoning there, but that seems to only happen in the case of the signals of signals, and those don't often come up when you're programming in Juniper, or if they do come up, you can work around them.
But you haven't explained why you need to lose equational reasoning, or how you lose it, or anything. You're just saying that you lose it, and that it's okay.
Yeah. So for instance, if you have I'm trying to think of an easy example here. So if you have a function which takes in a Boolean value, so on the true branch, it will count the number of clicks counted so far, and else it does something else. So if the value is false, then the true branch is never executed. So the number of button clicks will be incorrect in the case where the true branch is not executed. That's one example where you lose sort of the equational reasoning. Sorry, it's hard to explain without looking at an example that I didn't prepare for.
Yeah, fair enough. Maybe we should do this offline. But this is such a fundamental thing. I think that just glossing it over it in that way is maybe not the best way to treat it. What I actually challenge you to do is just figure out how to get the equational reasoning back. You're clever.
The problem is with space leaks.
But there's lots of work on how to get rid of space leaks in FRP. That's what should be upon.
Yeah, totally. Yeah, over here.
Can you go back to the blink thing?
The Juniper blink.
Yeah.
This slide.
Yeah. So So you're using a mutable reference to send the state of the LED, right?
That's correct, yes. The fold P function will mutate the reference that is passed.
Is it not possible to get around?
So if you look at programming languages like Elm, what happens is they can use they can construct a signal graph at runtime, which allows them to get around that sort of thing. Basically what happens is instead of a reference, you just pass high or low to the initial state, and it looks exactly like a list fold L or fold R. But secretly there's actually a state hidden behind the scenes. So whether or not it's explicitly represented.
So what
LED sig is sig of I of pin state.
This is all the pins.
Yeah.
And when you told you have the previous state of the tree from the output, right?
Yeah, that's an input to the fold P function.
There's a new input and the previous output. So why can't you just keep that rather than actually storing it in a reference somewhere?
I mean, it is stored in a reference.
But
So you have the state, both the input and output to the same analysis function. So,
like
well, the thing, so that change the code B to
What?
yeah, so that's an output, yeah. So that's to, yeah.
I could write a function in Haskell that takes a list of Boolean the XORs of the leftmost, so it starts at false and then it
Yeah.
true. And I wouldn't need to have a state that
Yeah, this is folding over time though, not over a list. So between invocations of fold P, those happen at different times. So there needs to be one specific place where the accumulated value is stored in memory between invocations of fold P.
so it probably can't store that for you.
Not like it can in Elm, no.
Is there a reason you shouldn't?
Is there a reason we shouldn't? It just doesn't work that way, I guess. Like I said, Elm does it differently. It constructs a graph at runtime, which allows them to get around that sort of thing.
It just seems like you've had this pattern where you have a reference either changing a lot. You just think, why not track that out to an operator?
I'm not sure what you mean.
Well, you always do it seems like a lot of the time you're going to be, the whole sheet is going to be modified some reference every time, right?
Yeah.
So why not extract that out into the,
Into
the way the function is making reference for you, a sheet by the side of the reference.
Could be possible. It's a good idea. I'll think about it, I guess.
To be more specific, instead of using fold P, why don't you scan P? So you'll have some signal coming in. You'll get out a signal consisting of Booleans,
Yeah.
and then have an operator to which you can feed that signal and it will drive the light.
So scan is reduce in other languages, is that right?
You're not familiar with scan. Scan is similar to reduce, except it gives you a list of outputs. So first does reduce over the first input, and then over the first two, and then over the first three, and so on. It gives you each of those reduces, but you can compute it much more efficiently than that. You can compute it in linear time rather than quadratic time.
Okay, I'm not familiar with the scan operator. Sorry.
Become familiar with scan. It's a great thing.
It keeps the history of all the reduces.
Yeah.
Jake, you talked about how the C program was like 950 lines, and the Juniper program is about a third as big.
Yeah.
Talk about the memory usage, because you know, in this whole conversation, a big part of it is how your compilers have been designed to be frugal on memory. So what's the comparison on memory between the two programs?
So are you talking about runtime usage or the actual compiled size of the program?
Cool. Just like how much of that 2K is used?
I'm not sure. I haven't actually done profiling on that. I know that the compiled size, the Juniper program, is about a third bigger, probably because we're using a lot of templated code.
So bigger than the C++ code?
Yeah, that's right.
So it's like it's a third shorter to write, but it's three times bigger to compile.
No, it's like 1.3 times the C++ code.
And no idea on the memory usage at runtime?
No. Sorry.
Okay, shall we move on?
So we actually have a bunch of Arduino kits that I put together, and we are going to write a sound visualization program. So if you all want to come up and grab a kit, that'd be awesome. We have some tables set up here now as well. Let me get the box.
Feel free, I guess.
Yeah, feel free to come up and grab one.
This is the demo part now.
This is the hands-on demo part. We're putting the work back in workshop here.